Thanks so much, Julie, and thank you all for joining us today. It's my pleasure to talk to you a little bit about some of the things that we've learned in high strength wastewater treatment. And we also have some poll questions that are going to come up throughout the presentation for you guys to also provide some feedback in terms of, what are some of the situations that people are running into and causing issues. So with that, we'll move forward, talk through kind of wastewater treatment specifically as it's applying into the food and beverage processing arena, and some of the challenges that we've learned from folks that we're working with, and how we could better manage these wastewater streams to reduce costs, improve sustainability, and ultimately, meet the critical metrics around business operations. So when we're talking about some of the challenges, right, what we've learned in our discussions and doing this now for a few years. So wastewater is highly variable depending on the production process, right? Whether it's a seasonal process, whether you're switching product, and or increasing product production. We saw a lot of impacts in COVID to different parts of production business, in terms of how things are bottled, distributed, and having to move things around, and that of course has an impact on wastewater generation and how that wastewater is managed. Um, of course, in every location, no matter where you are in the world, there's going to be permit requirements. So within your local municipality, within your state, within your country, there's going to be certain guidelines and risk mitigations that have to be addressed, even before you start operating in many cases. And then, many businesses have a direct eye toward meeting their sustainability goals, and oftentimes this is going to include water reduction. So minimizing the amount of water into the process, which of course is going to minimize the water out of the process. But that also has impacts relative to reuse applications, increasing the concentration of discharge at every plant, and that also impacts the cost in managing wastewaters. But water is a critical resource in food and beverage and around the world, right? So how can we all better and more sustainably manage this resource? And then finally, in many regions, um, you're going to face escalating costs, right? Whether that's an annual fee increase, whether there's, and that's distributed to all ratepayers or specific to food and beverage operations because there's an increase in production or change in what's going on the centralized treatment plant. But in many cases, you're going to see an increase in cost either in water delivery or in your sewer cost, water discharge, or in hauling rates if you have to land apply somewhere. So all of these things really make wastewater management a pretty complicated factor because it is very regionally specific. And so, the options that are available today. So if you're in a municipality with a centralized treatment system and a robust sewerage system, often you can discharge directly to sewer, right? And sometimes that centralized treatment plant wants really ultra high strength wastewater from food and beverage, right? If there's an anaerobic digester in place, if there's a large flow that's more dilute coming from other areas, that food and beverage wastewater has a lot of critical nutrients, right? Which is great for the centralized plant operation. But in some cases, especially in small municipalities, where the food and beverage operator may be discharging pretty significant volumes, the discharge to sewer can potentially cause problems to that centralized facility. So then the next option is having to truck this wastewater from the production facility off either to another municipality or to an alternative land application. And so there's obviously costs involved in that. There's tipping fees, there's hauling fees, there's ESG costs, carbon footprint, et cetera. And all of these things are going to add up, and not always having redundancy, right? So if a hauling company goes away or a certain municipality is no longer receiving this type of waste, you're stuck, right? There's a change that has to be made. And so then that's going to drive an evaluation of on-site treatment. So this is going to be installing some level of treatment plant within your operations. So directly at the discharge point, there is wastewater treatment, potentially, an opportunity for wastewater reuse as well, depending on where you are and what the goals are. But this is a major investment. And so, when it comes down to making these decisions and how you're going to move forward, there's a lot of things to take into account. And not the least of which is the technology, right? There are many technologies available within wastewater treatment. Some are newer, some have been around for decades and decades and are well accepted, but may be very costly. And so when it comes down to selecting the right technology, if you are going to do on-site treatment or even industrial pretreatment, right, and still discharging to sewer, but just decreasing some of that load, some of the considerations to keep in mind. What is your ultimate goal? What do you want to do with that water, right? Is it really you just want to reduce the cost and discharge? Do you want to reuse that water to drive down overall operational costs in the long term? How clean do we need to get the water in both cases, right? And then operational requirements. What are the restrictions relative to footprint, energy consumption? What would you want to do? Energy recovery, right? Are you looking at waste treatment as an option to provide renewables on site? What are the ultimate ESG goals, right? What are your carbon footprint goals? What are the water reuse goals, if any? And then also within the organization or even locally plant by plant, what is the ultimate expansion plan, right? Are you going to be adding production lines? Are you going to be expanding the size of the facility or changing a product? All of these things are really going to drive technology decisions. And so, when you're talking about some of the other things, if you're expanding or you're starting from scratch, your locality is really going to drive a lot of the specific selection criteria for the quality goals, right? But your technology selection is also going to fall into your compliance assurance and risk mitigation, making sure that you're always falling in line with that permit wherever you are. So it's a pretty complicated, matrix of decisions that have to be made. And so, but it's really important to start to begin thinking about things and the way that you can manage wastewater in the most cost efficient and environmentally sustainable way. And so, would love to hear from the audience relative to, your role and what you're doing in your business. What are some of the major factors that are driving your decisions? And Julie is going to be putting up a poll right now for you guys to respond. All right. All right, we still have votes coming in.
I'll leave it open for another 15 seconds and get any of those last minute votes. Definitely interesting to see what you guys are saying.
Great. All right, so the winner is permit compliance by a fairly wide margin, by 56%, followed by escalating costs, treatment upsets, and production limitations. Cool. All right, well, thank you very much for that. And that really falls in line with what we're talking about today, right? So a major driver being compliance, and then how do you drive down cost as you're meeting those compliance metrics? All right. So, when we're talking about costs and compliance, that brings in a lot of vocabulary. And, wastewater world, we like a lot of acronyms. So I'm going to go through a few that we're going to talk a lot about today. And I apologize to the audience that knows this really well, but it's always, occasionally good to have a refresher. So when we're talking about those things that you're charged for, right, in the wastewater space. So what you're trying to ultimately reduce is your volume, right? Because you're going to be charged by your total volume in a month, or your gallons per day on average, right, which is going to be metered out of your production facility. So that's one. You're also potentially going to be charged or surcharged for biological oxygen demand, or BOD. This is the regulated parameter across the board for how much carbon, essentially, is a soluble carbon is within your wastewater stream. And what BOD is, biological oxygen demand, is literally the amount of oxygen that would be required for bacteria to breathe to completely break down all of the soluble organics in your wastewater. So usually sugars, right? But there's going to be starches and some other components in food and bev discharge. So you're going to be charged by the pound in the US for BOD, or by the kilogram of BOD elsewhere. And that's a monthly bill, right? And that can be sampled however frequently the city decides to come out and do that, whether they've got an inline sampling device, or they come out quarterly or monthly or annually to grab a sample and say, okay, this is how much BOD is representative in that stream, and this is going to be your charge for the rest of the year or quarter or month, right? So that's how the rates are often established. Now, we as in the wastewater industry will often measure a proxy of treatment success by also looking at COD, chemical oxygen demand, which is really a broader look at the total carbon in the wastewater. So not just what the bacteria can consume in a 5-day or 7-day test, but literally the amount of oxygen that would be required to fully oxidize all of that carbon. So if you're going to combust it, as an example, right, how much oxygen would be consumed in that combustion reaction? So chemical oxygen demand, or COD, is really a much broader capture of how much of carbon is actually in that wastewater. Sometimes a municipality will charge you on COD instead of BOD, but that's rare. Most surcharges are going to be based on BOD, biological oxygen demand. The next thing they're going to be charged for is total suspended solids, TSS, which is a measure of all of the particulates in the water that exceeds a certain size, which is typically 2 microns. So this is another grab sample, right, which can be a composite sample, or it could be, periodically, sometimes throughout the year. And then you're charged per pound of TSS that was found to be in those samples that were collected, right? And then that's your rate. Then there's also, this other thing to take into consideration, which is fats, oils, and grease. There's not usually $1 per pound of fog that you're charged, but it can be a confounding metric, because often this is something that can be problematic within your collection tanks or your collection infrastructure, something that you may have to separate out on site anyway, and that's typically a hauling cost, right? So also something to keep in mind, depending on what it is that you're producing, how much fog is going to come out of the process, and then how are you going to manage that, either through the municipality or through an independent contractor. So this little cartoon here is meant to just sort of kind of walk you through all the different levels of carbon that you're anticipated to see in wastewater, and how you're going to be billed. So when it comes down to selecting a technology to deal with BOD, COD, TSS, and fog, right, you've got a lot out there. And there are selection criteria that are going to define your choice, right? And just as we talked about, right, permit compliance and cost. And then also, reuse might be a factor in that. So when you're talking about achieving the highest effluent quality possible for reuse, right, you're always going to need some level of, disinfection, tertiary treatment. It's usually going to involve a filter. You're going to need reverse osmosis, and then you have a very high quality effluent, which can be reused in various applications after full on disinfection. But before you get to that RO piece, right, you need some pre-treatment, and the technology selection can often be dependent on what level of COD or BOD that you're generating in your process. So if you're looking at really low levels to begin with, filtration steps are going to be, easy to integrate, easy to maintain, low energy. But as you start to increase in that COD concentration, you're really moving now into biological technologies which can help remove that organic. The DAF, dissolved air flotation, is really the tried and true if for removing fog, fats, oils, and grease. And then some of these other technologies can come in after that, further decrease your COD, BOD loading, and then followed by a polishing step, which could get you to some reuse activities. So you've got a lot of choices here. Some are aerobic and other, those that are anaerobically based, right, are the ones that are going to be addressing those really much higher concentration waste streams. So we're talking about CODs, well above 3,500 milligrams per liter. These are pretty common CODs that you see in food and beverage processing, getting up even into 30,000, up into the hundreds of thousands of COD, milligrams per liter. And so that's where the anaerobic processes come in. And really there's the tried and true anaerobic digester. There's now a lot of high rate anaerobic digesters out there, which have a good track record. Being able to process these wastewaters, usually in the 30,000 milligram per liter range, very effectively. But you're going to require a reasonable footprint. The other benefit for anaerobic digestion, whether that's an anaerobic membrane bioreactor or more conventional anaerobic digestion technology, is that you're going to be making methane, right? And you can capture that methane, go through a process of cleaning that biogas and reusing that, either through a process of cogeneration for heat and electricity, or direct injection into a natural gas line, using it on site, or selling it back to your natural gas grid. So that gives you another option for energy recovery, as well as being able to directly address these very high strength wastewaters. Where AquaCycle comes in, we are an anaerobic technology, but we go up another level in terms of the concentrates that we can address. And we do treatment in a very small footprint, but we're not actually making any methane. The power that is generated is as DC power, which can be used to charge a battery pack, and that can be used to offset basically the energy requirements of the system. We're not delivering a lot of energy back, although in some cases that could be enough to power charging stations, LED lighting, etc. So, across this whole span of wastewater technologies, right, what you select is really going to be based on what is your discharge quality, right? So knowing these metrics and understanding these metrics across your production cycles and across different products is really important. So you know what the variability is going to be. And then ultimately, right, what's your end game? Do you want to get to reuse? Do you want to just be able to reduce cost and stay within permit compliance, right? Within those two criteria specifically, that's going to really drive decisions, and the ability to select the best technology for your application. So, one of the things that we've started to notice across our work in this industry is that the large production facilities, especially, most of the volume that comes out of a larger production facility is already pretty clean. It falls in these low range concentration areas. But about 20% of the volume falls within these really high range areas. And typically, right, everything is coming off of a production line. You've got maybe a collection sump or a collection tank, and so everything is mixing at that point, and then you're treating your mixed wastewater, or you're sending your mixed wastewater off to either the sewer or whatever strategy you've got for managing that wastewater. So when you're mixing that 80% of not so dirty water with 20% of highly concentrated COD, right now you're elevating the amount of volume that has to be treated. But what if you just take that 20% and treat it, right? You're not decreasing the volume of discharge necessarily. Of course, it's still 100% of the volume, but you're only really having to focus on specific treatment of the most concentrated streams, which are going to lead to your highest BOD, TSS, and fog surcharges. So, just something to think about, especially on greenfield projects. If you start thinking about side streaming, if you start thinking about, how I can optimize CIP processes or capture, within the facility to just really, do an industrial pretreatment on that 20%, you can really reduce your overall cost and footprint and headache relative to wastewater management. So that's one of the things that we do. We focus on those concentrates because we're able to really work in that very high range of COD discharge. So acting primarily as industrial pretreatment in a pretty small footprint, right? We can take that 20% down to a level where when you're mixing it with the rest of your 80% volume flow, the dilution factor really makes a huge difference, and your surcharges go way down, 30 to 50% in some cases. And so, this is a plug and play technology that can retrofit into existing systems, whether you already have an anaerobic digester that maybe you want to enhance performance or increase capacity. If you're hauling and you're already side streaming and you want to eliminate that hauling process, right, that's something that we can help out with. And the other advantage to doing this, is basically separating your high strength and your low strength, is that it does also, have an advantage to those centralized treatment systems, which may be facing some burdens, right, and pushing back on those permits and increasing those charges for those permits, right? So you're still giving them the same volume of flow. So, if there's a centralized facility which is really focused on reuse, they still get the water, but you're taking out a lot of that concentration. So that centralized treatment facility can also operate with less energy and less overall chemical addition to treat the same volume of water, right? So it's a good cooperation. Now, this isn't going to be a fit in all cases, right? But something potentially to keep in mind. Another thing to keep in mind, we mentioned the optimization of existing digesters. Well, there's a couple of things that can be done. So digester systems work great, right? But they age. And often if you're increasing your production capacity, but your digester was sized, for 10 years ago production, it may be having a tough time keeping up. So instead of revamping the whole digester, you can add us as a pre-treatment step. We take out total sulfur, right? So you eliminate the sulfide issues, which are often common with anaerobic digestion. In addition, we'll take out some of that COD, and then convert that COD from sugars ultimately to a volatile fatty acid profile that is going to enhance biogas production. So we do two things, right? We'll take out that sulfide. We'll enhance the flow that can come through the digester, as well as the biogas conversion efficiency, because of the feedstock is now normalized to something that ADs really like. And so we've been validating how this technology works across different parts of the food and beverage industry, as well as in other parts of the wastewater industry, including swine farms, residential sewage, military applications. Most of the work that we've done in food and beverage, we're looking at bottling, breweries, and confection. And so, what we aim to do is provide a plug and play system that can really survive well in these variable production environments. We provide real-time monitoring and remote controls, so you don't need a full-time operator to have us there. And we provide a treatment service with a guaranteed compliance, right? So that's all scoped out in the scope of work. And our target is to save our customers anywhere from 20 to 60% against what they're paying now. So how the technology works, so it's a bioelectrochemical treatment technology, and it is literally a little black box. Uh, it is an anaerobic process. We're using naturally existing bacteria already present in the wastewater or sourced locally from your operational environment. We bring those bacteria into our BETT reactors, and they start to form biofilms or fixed films on the internal surfaces inside of each one of these units. What they do is they start using these surfaces as a way to respire or way to breathe. And in that process, they give up electrons. We move those electrons across a circuit producing DC power. And sometimes we generate enough power to be a little bit net energy positive, but certainly enough to run ourselves. And then that relationship between electricity production and treatment rate is such that the more electricity that we generate, the faster we make these bacteria breathe, and therefore the faster they eat. So more electricity actually means a faster treatment rate. And that's a little bit different than anaerobic digestion, because we're not trying to grow bacteria, we're trying to maintain bacteria at the highest metabolic rate possible. Similar concept to a high rate anaerobic digester, but it's a very different microbial metabolism because we're not making methane, right? We're making direct power. So we operate in a very different efficiency scale than digesters do. And so what we do is we take these units and we stack them together like Legos inside shipping containers. We have a 20-foot unit and a 40-foot unit, which can process anywhere from 5,000 gallons a day to 10,000 gallons a day, depending on what it is that we're treating and the quality that we need to achieve. We are UL certified in Canada and the US. And so, just to share with you some stories that we've put together, case studies working in a commercial environment. So specifically one treating a confectionery stream. In this particular case, right, there was a side stream already in place, and the side stream was being hauled off site because it could not discharge into the existing treatment facility, just too much sugar. So the production variability was quite high, ranging anywhere from 30,000 to 350,000 milligrams per liter of COD, and that could span within a 24-hour period. And the goal with this particular client was, to demonstrate that the technology can handle these variabilities, stay within their corporate sustainability goals, and save some costs relative to hauling. In addition, providing some security in terms of, being able to always have a solution for treating these waste streams, not dependent on a particular hauling company. And so we set up a small unit, which is a fraction of the size that we would for a standard unit. So inside this container, we only had 12 little of our reactors. Our BETT units are only about the size of a standard car battery, right? So you only have 12 of these. The actual treatment footprint inside this container is about the size of a Fiat, right? So that's a 4-hour hydraulic residence time. We're looking at overall COD removal across the span of operations. We're trying to make sure that we're not producing a lot of excess secondary biomass, which is another hauling issue, right? And then also quantifying the amount of energy that's being recovered from the system. So what we found is we could actually remove up to 50,000 milligrams per liter of COD in a 4-hour residence time, right? And that's higher than what you feed to most conventional anaerobic digesters. In terms of secondary sludge production, less than 1% of that carbon, which was treated and removed, was actually converted into secondary biomass that left the system. And then in terms of energy recovery, we were able to produce about just under 2 kilowatt hours per kilogram of COD that we treated. To put that into context, methane digester is about 1.2 or 1 kilowatt hours per kilogram of COD treated. For this particular application, what that translated into is about 22 kilowatt hours a day coming out of our little Fiat, right? We're treating this particular waste stream. So now if you think about scaling this up, right, at a full scale, say around 10,000 gallons a day, this would take four of our fully packed containers, and we could net generate about 2,000 kilowatt hours in a day, removing roughly 80 to 90% of the incoming COD. Now, we've also evaluated what happens within breweries, and breweries are an interesting use case because many of the larger breweries are already going to have a system employed. Anaerobic digestion has been a workhorse within this part of the industry, and will certainly continue to be. But sometimes there is a particular brand or particular process which can generate these very high waste streams that could potentially be problematic in higher volumes going to that anaerobic digester. And so that was the challenge with this particular customer. It was a very high fruit pulp application, lots and lots of sugar coming from that. So very high TSS and very high sugar. So the COD starting here was about 120 milligrams per liter. And so the challenge was, really understanding, one, is the volume that they're producing of this waste stream going to impact the existing digester? And so they were in parallel doing this test. And then two, can our technology help prevent the hauling of this wastewater, which was what was going on when we started this? And like many facilities, right, this is a seasonal product. And so you're going to see a ramp up and ramp down in demand on this and production of this throughout the year. And so the overall goal here, right, was to reduce savings cost, eliminate the hauling, and also, provide some additional sustainability relative to wastewater management. So we brought in our little demo. So this is what the skid looks like. We can do this in a container or just like this under a shade structure. What we were showing in this case was removal up to 25,000 parts per million, and we're starting with a lower concentrate than in confection, but we're still seeing very good removal rates in a very short period of time. TSS was very high here. This was all organic TSS, and we did an 80% removal also within that same 4-hour period. And then the net energy recovery was a little bit lower than what we saw in confection. This is a more complex waste stream. But we did manage to hit all the goals there. And so, basically industrial pretreatment ahead of the anaerobic digester. And while you see variable rates in those case studies, it really reflects the concentration and composition of the wastewater that we're treating. So if we're looking at, across a span of different applications within food and beverage, confection, soft drinks, starch, sugar refineries, different types of brewery effluents, right? You've got a broad range of concentration and composition, which is coming out of these production facilities. And that is going to impact the specific treatment rate, not only of our technology, but of every technology, right? And so really understanding the variability, how often are you going to spike at 350 milligrams per liter? Is this a daily occurrence, a weekly occurrence? Hourly occurrence, and that's going to be a big driver in what it is that you install. And same is true in all of these production units, right? It's you need to be able to plan for the worst, hope for the best, but you don't want to poison the system that you install by either undersizing it or installing the wrong technology that won't be able to necessarily keep up with the spikes and or recover from plant shutdowns, et cetera, which is another challenge in a lot of biological treatment technologies. So if we think about, the comparison between biological treatment technologies specifically, and this is very general, right? We're talking activated sludge, which is the workhorse in aerobic treatment, conventional anaerobic digestion, that multi-day methane production, batch conditions, and then our system, right? We are able to provide much lower sludge production, so your secondary biomass that you have to manage is reduced significantly. In terms of energy recovery, right? If we're just crossing the same load removal across all different technologies here, right? The energy consumed inactivated sludge is really high. You have to force air into water to grow up this biomass, and then that biomass, as it's growing, is consuming all of that BOD and COD. But you always have to have a very consistent, you know, aeration plan. And when you have a really variable waste stream, that becomes difficult to regulate effectively. And so then you may want to go into a more anaerobic approach, right? Where the fluctuations are still going to have an impact, but you have a longer residence time to absorb that impact. And the energy consumed is going to be lower, and you're actually going to recover some energy in the process with anaerobic digestion. That's as methane. And you can certainly be net positive in that type of application. With us in play, we have some of the lowest amount of energy consumed, mostly because we flow very slowly, right? This is a low pressure, low flow application. We treat smaller volumes, but very highly concentrated volumes. The energy recovery is really on par with digestion, but this is as DC power, so you don't have to permit methane and go through all of that classification. And the overall footprint can be much smaller because we can treat these concentrates very efficiently in a little tight bundle. And so it's also very scalable, right? The technology, it can be one container, it could be 2 containers, it could be 10, depending on what it is that you ultimately need to treat. And that's going to be driven really by your business criteria. What is the quality and what is the permit compliance that's needed? Is stream separation an option for you? If so, let's just treat that 20%, keep this small, keep the costs really low, right? And if you start to increase, if you're adding new production lines, if you're expanding on that facility, we can add more containers as you go. And that doesn't require additional infrastructure. We're not digging any holes in the ground. We're not occupying a lot of footprint. We do need equalization tanks, right? We do pH adjustment, and then the ultimate treatment. But this can be done in a very small space, depending on what it is that we're treating. So less volume means less equipment. Higher concentration enables that for our technology. And so that really brings us to the summary here. Wastewater is very local, and your costs are going to be driven by where you're operating, and all of that permit compliance is also going to be very local. And so, across a large organization that has operations and across the globe, right? Each plant is going to have really specific challenges. And so it's really important to understand those variables, prior to selecting a technology, because there's really not going to be a one size fits all solution. And so, as you're starting to make these decisions, we do encourage you to consider the 80-20 rule. Consider side streaming if you have an opportunity to do that. If you have an opportunity to retrofit an existing sump collection, with a Brix meter that diverts off your high sugar stream, and then every other part of that flow goes to your sewer. That's an automatic reduction in BOD. And then you can look to different technologies to treat that side stream with a much smaller footprint and potentially higher efficiency and lower cost. And the theme really here is there's more than one way to skin the cat, right? There's going to be trade-offs, and you have to just really prioritize based on your business goals. And it's really important to have those relationships with your local municipality where you are operating, to really understand, what are the challenges that you could be facing with future expansions or production changes in concentration. How is that going to impact your business? And that, how can the local municipality work with you to help solve these problems? And utilities are under constant regulatory pressure themselves. And so it's really important to keep up with them and have a good relationship with them, understanding what those permit restrictions are, what their capacity constraints are, so you don't run up into a massive surcharge cost that's a surprise, right? So with that, I'm very happy to answer any questions. And thank you so much for your attention. And please reach out if anything comes up, if we can help talk through any of these issues or decision criteria, or share more about our technologies. Thanks very much.
Yeah, so we're already getting a lot of really good questions coming into the chat or into the Q&A. If anybody else, has questions, go ahead and put them in into either the Q&A or the chat, and we'll try to get to them. If we don't have a chance to answer all the questions, we'll follow up with you separately and try to come back with the answers. But we've gotten a couple questions, Oriana, about the energy recovery and how it compares with an anaerobic digester biogas purification. So how do you compare with anaerobic digester in terms of energy recovery?
Yeah, and it really is a range depending on what it is that we're treating and then how that biogas is managed at the end of the anaerobic digestion, right? So on a conventional digester, if you're moving into a cogeneration application, you're kind of losing energy each step of the process, right? So biogas purification, then you're going into the cogeneration for heat and electricity, right? So you're about a 30% recovery efficiency in methane to electricity. And that gives you that range of about 1 to 1.2 kilowatt hours per kilogram that you're treating, right? So that's AD. So that's right, this category here, and that's reported in a lot of different publications and journals. With us, we're falling right in that very same range, right? So we're doing a direct conversion efficiency, or direct conversion into DC power. So you're bypassing the biogas purification step and the cogeneration step, but you do have to install a battery pack, right? And there's another level of permitting and complications that you have to consider in doing that. But then we're running off of that battery pack, and to improve the efficiency in recovery, right, we don't want to convert from DC to AC. So it's best if we can use that DC power locally for charging stations, LED lighting, things like that. So in terms of actual conversion efficiency of carbon waste into electrical potential, we're right on par with AD. But with both technologies, you have to consider how are you going to reuse that power, and what's going to be the best use case for you, right? Is it going to be AC steam boilers, or is it going to be DC charging stations, LED lighting, etc.?
Okay, great. We've also gotten a couple questions around the limits. So I'm going to combine two questions. One is any salinity or TDS limits per bed, and how does our system remove TSS from the wastewater? What are the TSS limits, and does it clog the bed?
Yes, thank you. So in terms of TDS, so dissolved solids conductivity, we love it. The saltier the better. We've actually tested up to seawater concentrations. We haven't tested brine yet, but when we have a higher conductivity of the wastewater or higher salt concentrations, that actually makes our batteries perform better because we've got more electrolytic activity. We do not remove any salts, right? So any TDS, as in sodium chloride, that comes into us is going to leave. We do handle some of the other soluble compounds like sulfates that we actually take out total sulfur. And from a nitrogen perspective, we reduce total nitrogen by about 30%. And the nitrogen form that leaves our system is as ammonium. So that's the TDS answer, right? We don't take out salt, but it doesn't impact performance at all. Relative to TSS, so total suspended solid, what we actually do, so we've tested up to 35,000 parts per million of TSS. So it's pretty sludgy, pretty thick, kind of a melted milkshake consistency. And we don't really have any problems there. Clogging is not an issue. Part of our service also is that, we remove any residuals in the reactors as either quarterly or annually, depending on what we're treating. And there's no charge to the customer for doing that. That's part of our service fee. So the breakdown actually happens because we are separating that solid retention time from the liquid retention time. But the solids in our unit, which are captured there, break down faster because of that electrolytic activity. So when we're talking about an 80% removal of TSS in 4 hours, some of that is because it's trapped, right? But if that were just trapping and not breaking down, that system would clog really fast. But as it is, we only have to actually remove residuals, not because of clogging, but because of slower flow. That happens either quarterly at the most frequent or annually the most common.
And that goes to a question about the maintenance requirements. In this case, it was a daily maintenance required, but obviously we're not on the daily level. I don't know if you want to say anything else around the maintenance necessary.
Yeah. So one of the advantages of the design here is that, well, we're doing real-time monitoring and controls, right? So we're real-time analysis on performance. And so we can catch any, slow flow, potential clog, decrease in performance on the, energy recovery side really quickly. And we can troubleshoot and fix most of that stuff remotely. In terms of regular maintenance, right, the periods that we need to be on site would be to remove those residual solids, making sure that the pumps are, in good condition, mostly preventative maintenance. And with the solids removal, right, with a really high TSS load, we would need to be out there quarterly and that's 35,000 parts per million or higher. If we're looking at lower, which more average range is going to be around 500 to 1,000 milligrams per liter TSS, that removal happens annually. And the nice thing about when we do that is actually because of the modularity of how these things are operated. As we're doing service, as we're doing maintenance or any type of repair, we can bypass just those parts of the system that are showing an error or require that regular maintenance. 90% of the system stays running while we're doing that repair, right? So you're never fully down as we're doing either regular maintenance or repairs.
Great. And a really good question that came in is how robust is the system? So for example, in response to organic overloads, temperature fluctuations, inhibitory compounds in wastewater and bacteriophages.
So relative to temperature, it is biological, right? So we need to make sure that our temperatures are above 10 degrees Celsius, 50 degrees Fahrenheit. We do that by heating and cooling the container. Sometimes we may need to heat and cool the wastewater coming in, and that is going to be the highest energy consumption, right, within our system is HVAC always. But we operate with really low power everywhere else, so it's really not much of a consumption even when you're at the peaks seasonally. So that's heating and cooling. We regulate pH, so we're pH that comes to us, right? We're just doing an auto adjust. The pH that's discharged out of our system is between 6 and 8. In terms of disruptors and things that can come to us that potentially disrupt the biology, the nice thing about a fixed film technology, which is true in our case, as well as upflow anaerobic digesters and more coagulated or membrane-based biological systems, is that once that biofilm is established, you can really treat it terribly, and it's going to come back. So we have run concentrated bleach through every manner of CIP cleaning product that you can think of. We've stressed the system through dehydration. So taking units offline, draining them, materials are still going to be somewhat hydrated, but you don't actually have constant flow through there or no flow at all, in fact. Then we put this system back into the treatment train and we see recovery within 24 to 48 hours in all of those cases, whether it's a chemical shock, you lack of flow, or you're coming out of batch. So we can handle those production variabilities in both flow and concentration, as well as the chemical shocks. In terms of batches, we haven't, we've had these units out in the field now operating for over 5 years at a pig farm. And we actually have not had to reseed the system. We haven't actually had to change any components at all except for the pumps. And so that's been a great life cycle test for us. We'll see, at some point we do expect that we may have to reseed that system, but so far so good.
And you're just talking through a bit around the flow, and a couple questions came in related to the maximum flow capability and whether it's flow or batch process.
It's a continuous flow during operations, but the startup phase is in batch. So it takes 1 month on startup to establish that biomass, to get those biofilms nice and fat and happy. And then we move into continuous flow. And the per container flow rate, right, is really going to depend on what hydraulic residence time do we need to hit the quality metric on the customer. So, if we're starting with 100,000 parts per million of COD and we need to remove 80% of that, we need a 9-hour hydraulic residence time. So that's going to minimize the amount of flow we can put through there. So a 40-foot container is going to treat about 5,000 gallons a day, right? But that's an 80% removal starting with a really high concentrate. If you give us a lower concentration, say 5,000 milligrams per liter per day, and we're doing that same 80% removal, we can flow 10,000 gallons a day through that same footprint, right? So it's really going to depend on what it is that we're starting with and how clean we need the water to be.
Right, and I think this question came from somebody who also said their daily flow is around 250,000. So in that situation, it would probably go back to what you were saying with side streaming and kind of the 80-20 rule.
Right, and that would be a question, is it possible to divert your first couple rinses of CIP and, any of those high concentrate streams into a much smaller volume? Because a majority of that 250,000 gallons a day is not going to be super highly concentrated wastewater, unlikely, right? So is it possible to do the split and then just focus on those concentrates on site, allowing a majority of that flow to go, with lower surcharges?
Okay. So we got a couple questions around different industries. So one was, have you tried the system on sewage? And then the other one, maybe somewhat related but somewhat different, was around non-food waste. So like pharma, will it handle aromatic compounds, phenols, anilines, et cetera, non-food wastewaters?
Yes and yes. So from a sewage perspective, we have trialed this system. Actually, we've most of our data is started in sewage treatment. So we've done some work in Tijuana, Mexico. We've done some work with the U.S. military looking at sewage sludge and remote operating bases. And the technology works quite well. In fact, for some water quality metrics, we actually hit irrigation or even sometimes drinking water quality in terms of BOD removal. You still need disinfection, you still need post-treatment, there still needs to be other technologies post us. But from a removal perspective, the technology works very well. But you have to consider the flow rates typically that you see in large centralized facilities. They're going to be millions, hundreds of millions of gallons a day, right? And that's going to be a whole lot of containers. So our approach into distributed wastewater treatment would be as a replacement to septic or small community type things, but there's a lot of regulatory hurdles to pass before we could be used within that market. A lot of demonstration that needs to be done, and that is also very regionally and locally specific. Relative to other waste streams. So yes, we are able to degrade hydrocarbons, gasoline, diesel, benzene, phenol, in some cases below detection limits for the tests that we've done. We've also looked at natural and synthetic estrogens, painkillers, some of these emerging contaminants. While the technology, we see a disappearance of these compounds, it's hard to know if it's because there's just an absorption, right? Because a lot of those compounds just like to stick to surfaces, or if in fact we are breaking them down. And at least that's the case in some of those other more exotic contaminants, hormones, etc. So it does work well in a lot of those applications, and we've done some work with the U.S. Army on battlefield hospital waste and things like that relative to the pharma question. There needs to be more trials done to really prove it out in that industry.
Okay, well, we've still got a lot of really good questions, and unfortunately we're out of time. So what I will do, Oriana, could you put up your last slide? I think it has your email address. And we'll try to come back directly to anybody whose name and email addresses were included and answer these questions that didn't get answered. If we miss you, or if you have any other questions, you can follow up directly with Oriana. Or you could also email info@aquacycle, and that usually gets answered really quickly as well. So thank you everyone for joining. We loved all the fantastic questions, all the engagement, and we really appreciate your time and look forward to further discussions at some point.
Thanks very much. Hope to see you soon.
Bye. Thank you.